The Indian Machine Tool Manufacturers Association, IMTMA, providing the cutting edge to India's machine tool industry. IMTMA was formed in 1946 with a vision of providing a one-stop impetus for the machine tool industry in India, spearheading India into the forefront of industrial revolution by providing a platform for symbiotic industry growth and innovation-led machine tool technologies. What's more, IMTMA has today become a center of excellence for focused application-based training.
Welcome everybody to the online training programs from IMTMA. A very quick overview about IMTMA. The full form of IMTMA is Indian Machine Tool Manufacturers Association. We were set up in the year 1946 as a machine tool member organization. Today we have close to 470 plus members, and we take up multiple activities which include government advocacy on behalf of the members. We conduct a number of corporate training programs. We organize the IMTEX Machine Tool Expo annually. And besides that, we conduct a lot of training programs where we are focused on enhancing the competitiveness in manufacturing. We have conducted over 126,000 plus man days of training so far, with a portfolio of 200 plus standard training programs, over 4,500 companies whom we have trained till date, and with a participation of over 32,000 professionals so far. Our technology center in Bangalore and the technology center in Pune, and each of these facilities are fully equipped with all the requisite machinery, metrology equipment, accessories, automation lab with robot, and is completely Industry 4.0 ready. We deliver our training programs in 4 different ways: short-term programs, in-house programs, e-learning, and long-term courses meant for young graduate engineers. Our classroom training programs are delivered by experts who have experience in excess of 30 years, with a blend of theory and hands-on training wherever possible. We supplement the programs with demonstration of live machinery or industry visits wherever possible. And we encourage a healthy interaction between the participants and the faculty through the program. Our e-learning initiative is delivered through an exclusive e-learning portal, and the current portfolio is about 10 programs which can be accessed by the participants at their own flexibility during the license period. And the entire program can be taken at their own convenience and flexibility, with assessment, evaluation, and certification being provided through the e-learning platform itself. Ever since April 2020, we have come up with the online training initiative, and till date, we have completed over 300 programs, addressed over 15,000 participants, and we have made these programs easily accessible to various types of participants, which can be taken up at a minimum training budget. And we enable live instructor-led programs with interactive question and answer sessions, polling, chat box, and we also provide live demos wherever possible during these training programs. Long-term programs are primarily meant for young graduates who wish to improve their employability prospects by taking up a few programs on design, production, automation, FEA, and these programs are available in long-term mode for young engineers. We thank you. Please visit our website, imtmaelearn.in and imtmatraining.com.
So welcome to this very short program of IMTMA, which will try to give you a brief on how we can go around measuring the capability of various processes. Yeah, so how to measure process capability is the topic of this very short webinar. Of course, this is part of the whole gamut of what we call as statistical process control. We are going to talk about a very short portion about the process capability measurement. So today, most companies and countries are talking about world-class manufacturing, that we want to move towards world-class manufacturing. And we talk about world-class manufacturing, we are actually talking about having cost and quality targets which need to be met. Sometimes people feel that it is not just cost and quality, but much more than that. But if you can achieve the cost that your customer is willing to pay for the quality that you give him, then you are on your way towards a world-class manufacturing system or a process. So with bearing this in mind, there is no point in producing a quality which a customer is not willing to pay for. Or otherwise, if you have a great quality, but an exorbitant cost, that also a customer is not willing to pay. So achieving the targets of cost and quality together are the keys to world-class manufacturing. And that is what most companies today are aiming for. The journey normally starts by eliminating the non-conforming parts, or what we call as rejects in our process. We ensure that the rejects don't go to the customer, be it an internal customer or an external customer, because rejects means, first of all, that you produce a part which you cannot pass on, you cannot market it, you cannot sell it. So whatever cost you incurred in making or manufacturing that part is a waste, which ultimately results in a higher cost of manufacturing, which reluctantly a customer may pay for. But if your competitor is better than you in terms of quality and cost targets, then you lose out on business. So we ensure through our SPC or through our process control or quality control, we ensure that we do not pass on non-conforming parts to our customer. However, when we make a process which produces non-conforming parts and conforming parts together, it means that our process has too much variation. So the next step in our journey would be to reduce the variation in the manufacturing process itself, such that we do not produce non-conforming parts at all. So this is the most important step in our journey to world-class manufacturing. And this means the control of the process itself. So moving from elimination of non-conforming parts to reducing the variation in the process to controlling the process is the journey for world-class manufacturing. So when we talk about controlling the process, we cannot control anything unless we measure it. So measurement is a key to control of process. Now, if you look at these images, you see various things in here. On one side, you see rework and scrap, and this adds to the cost of quality. Rework means that you need to spend more time in correcting what has gone wrong. Secondly, it also reduces the quantity of good parts, which then have to be shipped to the customer. And especially if you have an export customer, the situation becomes worse because you might have to expedite the delivery. You may have to air freight things or express delivery. All these add to cost. And a very big cost would be if this problem of quality is seen at the customer's end, your end customer, and you need to do a replacement, like the knee replacement, it's a very costly business. Not only it's very costly, it also means that at the end of the day, your customer is not happy with the situation, because all this results in higher cost, and ultimately this cost would be borne by the customer. So anything which is helping you to measure and control your process would end up resulting in reducing the cost of quality. Since the Olympics are going on, I thought I would take a small example from the Olympics. I'm sure a lot of you are following the Olympics, the archery and the shooting. So here you have a bullseye, and in this bullseye, our archers and shooters have to shoot. And we have our good friends, Mr. Vishnuji. So Mr. Vishnuji does some shooting. And let me show where he shoots. So this is what our good friend Vishnuji is shooting. So this is what Mr. Vishnu has shot. And then we have another good friend of ours. I think Mr. Bhupendra is around. So Mr. Bhupendra shoots. And probably they get 100 shots. I'm just marking a few, for example. So this is what Bhupendra ji shoots. So now the question that arises is, who is a better shooter? Is it Vishnuji or is it Bhupendra? I'm sure a lot of you will say that it is Vishnuji who is a better shooter, because his shots are in a cluster which shows that the process has less variation. But unfortunately, it is Bhupendra ji who is going to win the medal, because he reaches the target more often than not. So the answer to this question of who is a better shooter really depends on what you want to achieve. There could be one more shot, and that shooting could be somewhere here. So we have three types of shooting that could have possibly happened, which I would call as different causes in the process. So what Mr. Vishnuji has shot possibly has some kind of a special cause which prevented him to shoot and come to the center of his process. So his process centering could have well improved, and then he could have got his gold medal. Bhupendra ji has too much variation in the process, and if Mr. Vishnu ji had collected his process to the center, he would have won the gold medal and Bhupendra ji would be out. And of course, the third one, which is out here, which is totally off target. So in the language of process capability and SPC, we talk about three possible variations or three special causes, three causes. So what we call as Vishnuji's are what are known as special causes. Bhupendra ji has common causes. And this one out here is what we call as outlier. So we have these three types of variations which could have possibly happened in our process: the special causes, the common causes, and the outliers. However, if we allow many shots over a period of time, I'm sure Vishnuji would have corrected and brought his process to the center. Similarly, Bhupendra ji could have possibly made improvements in his process, and hopefully the person who shot an outlier would have corrected his thing. Then over a period of time, we find that in most processes, we have a distribution which we call as a normal distribution. So normal distribution is a distribution which is of a frequency distribution. And in this case, the frequency distribution of Bhupendra ji would look something like this. and that of Vishnuji would look like this. So this shows the variation in Vishnuji's distribution is of a much lower amount as compared to Bhupendraji. So in our terms, we call this as sigma or standard deviation. So standard deviation value is a measure of variation, and that variation in case of Vishnuji is a much less than that of Bhupendraji, though Vishnuji has drifted away from the target. So ultimately, in our processes, we would like to produce only conforming parts, in which case Vishnuji would produce some non-conforming parts, even though his variation is low. I hope this is understandable to most of the people out there. So this normal distribution has some interesting properties in it. So if you plot this normal distribution and you divide it into different zones, so you have the mean, which is at the center here, and then on both sides you have plus sigma, or the plus the standard deviation and minus the standard deviation, and then this area which is under this curve corresponds to around 68% of the distribution. If you then take further up to 2 sigma and minus 2 sigma, we cover a further 95% of the distribution, that is the area under the curve. And if we take up to 3 sigma and minus 3 sigma around the mean, we cover 99.73% of the distribution. What this means is that if we have sufficient data, and if our distribution is that of a normal distribution, which is there in many cases, we would be able to predict that 99.73%, where would the short lie within the plus minus 3 sigma limit. However, you must also note that there is a 0.27% which goes beyond the frequency distribution as shown here. So to summarize this, the normal distribution has some interesting properties, of which 68% of all the numbers or the area under the curve falls within the plus minus sigma. 95% of all the numbers or the area under the curve will fall within plus 2 sigma and minus 2 sigma. 99.73% of all numbers will fall within plus minus 3 sigma. However, 0.27% falls beyond plus 3 sigma or less than minus 3 sigma around the mean. So this being the mean, we are able to now project and predict what our process is likely to perform in terms of its quality. So this is only true for normal distributions, is something that you must remember at all times, because there are many cases, or a few cases at least, where the distribution may not be normal, and this rule that we have said, or this areas under the curve, will not follow this pattern. So to estimate the standard deviation or sigma, there are two different methodologies which are used. So when on an ongoing process, we plot what are known as X bar R charts. So if you plot these charts, X bar and R charts, then you can calculate sigma is equal to R bar by D2. Now, the plotting of these charts, just to explain a little bit, try to imagine that you are in front of a process. Maybe at 7 o'clock in the morning, the shift starts, and you take a sample, say, of 3 pieces, and you find out the average or mean of those 3 pieces. This is X bar. Now, you do the same sampling at every half an hour interval. So 7 o'clock, 7:30, 8 o'clock, 8:30, and so on and so forth. And you keep plotting these X bars. So this is your X bar chart. Also, you take the maximum and minimum, the difference between the maximum and minimum of each sample, and plot that. And that is known as the range. So that is the R chart. So first is the X bar chart. This is the X bar chart here, what I've shown here. And here you have the R chart. Now, a process has its own inherent variation. Every process has one. So what we can do then is plot the plus 3 sigma and minus 3 sigma limits. So the upper control limit is the plus 3 sigma limit, and the lower control limit is the minus 3 sigma limit. Same is the case with the range chart as well. So we have the mean here, X bar, and we have the range here, which is the R bar. And then we calculate the averages of R's, so that is the R bar, and then we can calculate the R bar by D2. Now, please note that as long as these plots lie within the control limit, it shows that there is no special cause variation. In Vishnuji's case, we saw that there is a special cause variation which has triggered his shots away from the center of his target. So in that case, his plots would go above the upper control limit or the lower control limit, and it would indicate that some correction is necessary. In case of our friend, the second person B, the plots would lie within the upper control and lower control limit, which means that he is lying within the plus minus 3 sigma limits, and we are able to predict what likely is he able to shoot over the next, say, maybe 10, 15, 20 shots. So this is how control charts are used to predict the process. So it's a measurement of the capability of the process. But please note, this has nothing to do with what you expect as a customer. We are only talking about the variations, inherent variations of the process caused by common causes. So this is the method of measuring sigma and finding out the limits plus 3 sigma and minus 3 sigma, so that we are able to predict where our 99.73% of the parts will lie. That means that many conforming parts this process will continue to process and to manufacture over a period of time. There is another way to measure the standard deviation, and that is by a formula, and that's sigma. To differentiate from the other one is sigma s, which is under square root of xi minus x bar square whole square, sum of all xi and x bar square divided by n minus 1. Now xi here is an individual reading. X bar is average of all those readings. Each of them is squared, and then you sum all of them and then divide by n minus 1 and take the square root. So this is known as the total process variation. So now you can imagine that unlike a control chart, here is a case where you have a bin which may be around 500,000 pieces lying in it, and you are drawing from it a sample maybe of 50 pieces or 100 pieces, measuring each and every one of those sample pieces. Find that is the xi. Xi means x1, x2, x3, etc. Finding out the difference between averaging all of them, that will be the x bar. Finding out the difference between x1 and x bar and squaring it, and adding to that x2 minus x bar and squaring it, and so on and so forth. So you add all of them, you divide by the total number of the samples that you drew, that was n minus 1, and take the square root of that. And this is your sigma s. So here you are not really worried when those parts were being produced. So this is not for process control, but this is a post-mortem exercise to find out the quality of the parts in a lot. So this is the difference between sigma and sigma s, and we will see how we use sigma and sigma s in the next few slides. So now we know what my process is capable of producing. The next part is I would now like to know, will it produce good parts for me in future or not? Which means I must compare what my process is capable to the target itself. So this is what is known as the process capability index, or CP, for a statistically stable process where sigma is estimated from the control charts. So here CP, formula for CP is the total tolerance divided by 6 times sigma. So if CP is greater than 1, which means that the tolerance is greater than 6 sigma, which means that you will get 99.73% parts which are okay in the process. So this is how a process capability index is worked out, and this is how you measure process capability of a particular process as compared to its tolerance. So I hope it is clear that we are trying to here compare the tolerance, that is what the customer wants, to what the process is capable of, which is 6 times sigma. So CP greater than 1 would mean that we will get 99.73% parts which are correct. Now, this is also known as short-term process capability index because this exercise is done from control charts over a short period of time. However, if this exercise were to be carried over a much longer period of time, maybe a month or 2 months, and we had got all the excise, that means all the individual readings of the parts, then we would use sigma s by that formula rather than the CP. So here it will be the PP that we will calculate, which is the tolerance divided by 6 sigma s. And this is the long-term process capability index. So this is the long-term process capability index, and that is also known as the process performance index. So the difference between the process capability index and the process performance index is, the difference is the use of sigma s, which sigma s we are using. So if we use sigma, then it is CP. If we use sigma s, then it is PP. Now, if we move forward, there is another index called CPK. Now, this index of CPK tries to find out what is the difference if the process shifts away from the center line. So if the process shifts away from the center line, that means your process centering and your tolerance centering is not the same, then what happens? So what happens in this case is that we measure 2 indices, CPU and CPL. So the formulas for these are CPU is USL, or upper specification limit of your tolerance, minus X double bar, or the process center, divided by 3 times sigma. The CP lower, or CPL, is X double bar. X double bar minus lower specification limit or the lower value of your tolerance divided by 3 times sigma. And what we do is we, after calculating CPU and after calculating CPL, we take the lower value of the two. So if CPU is greater than 1 as shown here and CPL is less than 1, then CPK will be equal to CPL, which means that we will still, even though CP may be greater than 1 or equal to 1, we may still produce certain tolerance, certain defects, defective parts which are shown here. So in this area, because this has gone beyond the lower specification limit. If CPU is less than 1 and CPL is greater than 1, then we would know that our process center has shifted towards the upper specification limit and we are likely to produce non-conforming parts above the upper specification limit. So this is how one uses the process capability index CPK. Corresponding to CPK, we can also have a PPK wherein we have PPU and PPL. The formulas are all the same, only the sigma is different, in which case for PPK, we would use sigma S in place of sigma, which we are using for CP. So CPK is a process capability index, a measure of process capability index, which tells you if your process variation is within the tolerance or not, and to what extent is there a shift of the process as compared to the tolerance mean. Now, different processes you may also have where you can have in production, we try to maintain a CPK which is greater than 1.33. The reason for doing that is that if we maintain 1.33, that 0.33 allows us for process shift during the running of the process. That means the centering of the process can shift, and because of that centering of the process will shift, we provide that 0.33 as a safety margin. So in production, we aim at CPK values of 1.33. If you go in for a new equipment or new machine, we aim at a CPK value of 1.67, because you still want, maybe after 2 years, 3 years, or 5 years, that your process should continue to produce conforming parts and your rejection level is under control. So over a long period of time, there may be many more variables acting in the process. The equipment itself may deteriorate over time due to wear and tear. So because of all these reasons, we aim at much higher values of CPK. So this is how we measure process capability index, CP, PP, PP being the process performance index. We also measure CPK and PPK. So with this very short introduction of measurement of process capability,